Hello everyone! Today we will be covering Thermodynamics Lesson 5, Engines, Heat Pumps, and Refrigerators. Now, this lesson is not how refrigerators actually work, which means we won't be covering the individual components of a refrigerator and the actual cycle that it goes through. This is the theory behind how they work and how you can find the efficiency or coefficient of performance for these cycles. So, first things first, we shall cover engines. Now, if you recall, all processes that are real are irreversible. However, since we're just going over the concepts for engines, heat pumps, and refrigerators, we are going to go under the assumption that any process we have will be reversible, or an ideal cycle. We're going to operate under that assumption. So, when you're covering the engines, heat pumps, and refrigerators, you're going to have one type of cycle that is the most basic you can cover and encompasses the entire theory behind engines, heat pumps, and refrigerators, and that is what is called a Carnot cycle. Now, a Carnot cycle is the best cycle you can possibly create when you're creating these type of systems. A Carnot cycle has the highest efficiency or highest coefficient of performance, and is just in general the best you can do. So this is the most ideal cycle you can have. So this is a good way to explain the concepts behind our topics today. So what makes up a Carnot cycle? Well, a Carnot cycle has four processes. It has two adiabatic processes and two isothermal. Now you may be asking, what is adiabatic? What does that mean? Well, that just means there is no heat change between our system and the surroundings. So Q is equal to 0. Alright? You need to know what adiabatic means. It is very important that you acknowledge that adiabatic means there's no heat change between your system and the surroundings, because adiabatic is going to be used all throughout your thermodynamics analysis. So then let's draw the basic Carnot cycle. We're going to do it for an engine. So first off, I'm going to draw my PV diagram here. PV, and then if you recall, in the PV diagram I have isothermal lines. Now a Carnot cycle operates between two different temperatures. So I'm going to start here. This can be my point 1. I'll start over here. Point 1, point 2, point 3, point 4. So this is your Carnot cycle for an engine. And you know it's a cycle because it goes from 1, 2, to 3, to 4, and then back to 1. It's a cycle that keeps going over and over again. So 1 to 2, that process is adiabatic compression. Because you notice my pressure is increasing and my volume is decreasing. It may be very small due to my drawing, but you'll notice my volume is going to the left and my pressure is going up, so it's compression. 2 to 3 is isothermal expansion. Here I am expanding from point 2 to point 3 along my T hot, which is my high temperature, and during this entire process my temperature does not change. So then from 3 to 4 I have adiabatic expansion, and then so as you can see my pressure is decreasing and my volume is increasing. I am expanding my system. And then from 4 to 1 is isothermal compression. Sorry about that. 4 to 1 is isothermal compression. All right, these are the general, this is a Carnot cycle. It's going to have 2 adiabatic, 2 isothermal, and in this case it's going from 1 to 1 to is adiabatic compression, 2 to 3 is isothermal expansion, 3 to 4 is adiabatic expansion, and 4 to 1 is isothermal compression. All right, so if I were to draw it out, I would have my first piston here, and I am compressing the gas. So my gas here is getting pushed together, close together. Then this is 1 to 2, which is adiabatic compression. Q is equal to 0, no heat exchange between the surroundings. Now, this is going to be isothermal expansions, the next step. So here my piston going up now. My gas is expanding. This is 2 to 3 isothermal expansion. And this process is where heat is added to my system. My temperature does not change. So if you remember my first law, delta U is equal to Q minus my work. If my temperature does not change, that means my internal energy of my fluid also does not change. Therefore, my delta U is 0, and any heat added is equal to my work. Now, the next step is from 3 to 4. That is adiabatic expansion. So I'm here. Three to 4, adiabatic expansion, and gas expanded more. Q is 0, and now I'm alternating between, I'm going from my high temperature to my low temperature. All right? So this means that for first law, delta U is equal to Q minus work. Q is 0, so delta U is equal to my negative work. Oh, for here 1 to 2, adiabatic compression, delta U is equal to Q minus work. Q is 0, so again, delta U is equal to negative work. So let's have the final step, which is 4 to 1, which is isothermal expansion, or isothermal compression, sorry. So now I'm compressing it again. My piston is coming back down. This is getting more compressed. 4 to 1 isothermal compression. Since I'm isothermal, delta U is 0, and this is when heat is leaving the system. So I have Q out like that. So I have first law, delta U is equal to Q minus work, isothermal, so no change in internal energy. Q is equal to work. So this is a Carnot engine. Now, Carnot engine, again, is the simplest type of engine. It's the most ideal engine you can make. So it's going to be the engine that has the highest efficiency you can get between two temperature differences. Because remember, according to second law, to get work out of a system, you have to have heat or energy flowing from high to low. So if you have your high system and you have your low system, you can use the Carnot engine to determine, okay, this is the highest efficiency I can possibly get. And we'll be doing some examples of that later. So, well, I said you could determine the efficiency. how do you determine the efficiency? Well, you can do, if you recall, the efficiency is equal to the work out over heat you put in. Well, or the heat of the cycle. No, heat you put in. Well, if you recall, I'm going to have some heat go into my system from, if I draw this out, T high, and then I have here T low, and I have my box. That is my component, and I'm going to get some work out. Well, I have some heat entering the system, and then I'll have some heat leaving the system, and out of that heat difference, I get my work. Now, I'm extracting my work energy from the energy that comes in. Therefore, to find my work, it's Q high, my input energy, minus my output energy is equal to my work. So, if I can do the efficiency is equal to Q hot minus Q cold over Q hot, which is Q in. Now, you can do this specific part here that I just circled. You can do this for any engine you want. This is nothing specific to the Carnot. What follows is very specific to the Carnot. I'll just finish this. It's equal to 1 minus QC over Q hot. This is nothing different. You can use this for any cycle. But the next part is very specific only to Carnots. In the Carnot cycle, the relationship of QC of Q out to Q in is equal to my temperature low over my temperature high. This is only for Carnot cycles, all right? Only for Carnot. Therefore, I can rewrite my efficiency as 1 minus Tc over Th. And this is the maximum efficiency I can achieve. Now, remember, this is the best ideal cycle you can have. You're not going to have an ideal cycle, you're going to have a real cycle, so you'll never achieve this efficiency. But it allows you to plan and determine if whatever temperature differences you have set up is enough for you to, or is efficient enough for you to want to pursue that. Like if you get your temperature differences get you an efficiency of 30%, well, that's very, very low. Therefore, I'm going to want to increase that temperature range to get a higher efficiency. Well, now we shall cover refrigerators. All right? Right, that is a, nope, not the one I want. I want a stroke eraser, there we go. All right, refrigerators. Now, refrigerators are, you want to remove heat from a system. And it is, so you're pumping it back. You're pumping heat from a colder area to a hotter area. Now, if you recall from second law, that doesn't spontaneously happen. But if you put work in, you can make it happen. So, if I draw out my Mach cycle again, T low, my box, and I have QC going in and Q hot leaving, if I put in work, then this is now possible, and that is how refrigerators work. Well, since this is my body here, I want to remove heat from the system, so my input is my work, and my output is how much heat I remove. So my equation would be, since it's output over input, my equation would be QC over work. Now, when you're dealing with refrigerator cycles, to determine how good that cycle is, you are going to use what's called the coefficient of performance. C, sometimes called COP, sometimes denoted with this B value. And like I said, that's your output over input. What do you get out over what you put in? Well, I'm removing heat and I'm putting in work. So that would be my coefficient of performance for a refrigerators. Now, if you notice, refrigerators are just the reverse of an engine. So a Carnot refrigerator would simply be this cycle up here operating in reverse. So it would go 1 to 4, 4 to 3, 3 to 2, 2 to 1. I will do a problem with refrigerators, engines, and heat pumps after I get through this theory. Now, the next thing is a heat pump. Well, what is a heat pump? A heat pump is you're pumping heat into a warmer area. So you have this exact same drawing as a refrigerator, except this time our output, what we care about, is how much heat we add to that hotter system. So that would be QH this time. But our input is still work. Remember, a heat pump, you're pumping heat into the hotter system. That is what you want to do. A refrigerator is you want to remove heat from the colder system. Even though they have the same drawing, they're used for two different reasons. So again, you would still use the coefficient of performance for your heat pump, and your heat pump coefficient of performance would be Q high over work. All right, so remember, you can again turn this into Carnot, going up here and using this relationship here and this relationship here. Now that the theory has been covered, I will go and I will solve some example problems to show you how to use these type of systems. Okay, so let's do our first example. So we have an engine that operates between 1000 degrees Kelvin and 400 degrees Kelvin. 325 kilojoules of heat is supplied to my engine, which outputs 200 kilojoules of work and rejects 125 kilojoules of heat. My question is this engine possible? Well, first things first, I have to check, does this add up? Does this satisfy that my heat in minus my heat out equals my work? Well, I have 325 kilojoules in, I have 125 kilojoules out. That gets me 200 kilojoules of work. So far it's possible. Now, efficiency-wise, is this possible? Because remember, the Carnot has the highest possible efficiency I can get. So I need to compare this efficiency of this engine to a Carnot engine. So let's find the efficiency of this engine. Well, efficiency is equal to out over in, so work over Q high, which is equal to 200 kilojoules over 325 kilojoules, which will get me 0.615, which is 61.5% efficient. Okay, so that's the efficiency of this engine. So what if it was a Carnot? Well, if you recall from above, the efficiency of a Carnot engine is 1 minus the ratio of the temperatures. So I have 1 minus T low over T high. This is equal to 1 minus 400 over 1000, which is equal to 1 minus 0.4, which is equal to 0.6, which is 60% efficient. Now, as you should have guessed, the answer is no. This engine is not possible. Even though I can extract that much work from, no, I cannot, even though the work math adds up, this math adds up, my efficiency of my engine is higher than the efficiency of the Carnot, and remember the Carnot is the best I can do to get an engine. Therefore, this efficiency is not possible for between these two temperature differences. Therefore, this engine, it cannot supply 200 kilojoules of work. This engine is not possible. Or I cannot get 200 kilojoules out. I will get less than 200 kilojoules out. Okay, next question. I have this refrigerator. I am pumping in work. I have a cold area that's negative 30 degrees Celsius and a hot that's 30 degrees Celsius. I want to find my coefficient of performance for my Carnot refrigerator and my coefficient of performance for my Carnot heat pump. So for the refrigerator, if you recall, it would be the, I should change that to black, equals the heat rejected versus the work I put in. Now, I don't know what that is. I don't have any values here, but I know those temperatures, and this is a Carnot refrigerator. So I have QC over Q high minus QC. This is going to equal to my, if I divide them both by Q high, I get QC over Q high over 1 minus QC over Q high, which is equal to TC over T high over 1 minus T low over T high. Now, you may have noticed that I have these temperatures here in Celsius. Well, this doesn't work for Celsius. It has to be in the absolute temperature, which is Kelvin. So this in Kelvin is 305 Kelvin. This is 245 Kelvin. All right? So I want to then do this. I have my coefficient of performance is equal to 245 over 305 divided by 1 minus 245 over 305, and that is equal to, one moment, this is equal to 4.08. So that is my coefficient of performance for my Carnot refrigerator. Now, what about my coefficient of performance for my Carnot heat pump? Well, it will change because I am analyzing I am no longer analyzing how much heat I remove from my lower body. I'm analyzing how much heat I give off to my higher body. So my coefficient of performance is equal to Q high over the work I put into it, which is equal to Q high over Q high minus Q low, and then this can be Q high over, factor out a Q high, 1 minus Q low over Q high. Well, that turns to 1. So my coefficient of performance for a Carnot heat pump is 1 over 1 minus Q low over Q high. This is actually just for coefficient of performance for just a heat pump in general. Now, this is going to be the coefficient of performance for a Carnot heat pump, which will be 1 over 1 minus T low over T high. This is the coefficient of performance for a Carnot heat pump, which is what we want. This is the coefficient of performance for just a normal heat pump. So I have my coefficient of performance is equal to 1 over 1 minus 245 Kelvin over 305 Kelvin, and this is equal to, having technical difficulties. Here we go, is equal to 5.08. Notice how my coefficient of performance for my Carnot heat pump is higher than my coefficient of performance for the Carnot refrigerator, because I am rejecting heat from my engine into my, or pumping heat into my hot body, while in the refrigerator, I am removing heat from my lower body. They are two different systems, even though they have the same thermal diagram. All right, thank you very much. As always, if you like the video, please subscribe, and if you have any questions, I'll be happy to answer them in the comment section. Have a wonderful day.